300 million. That is the current scientific estimate for how many potentially habitable planets exist in the Milky Way alone. 300 million worlds orbiting at the right distance from their stars. 300 million chances for oceans, atmospheres, chemistry, and life. And the number of those worlds that have shown a confirmed sign of life is zero. Not one verified biosignature, not one confirmed radio transmission, not one artifact, not one unmistakable signal that says someone else made it. For more than 60 years, humanity has pointed increasingly sensitive instruments at the sky: radio telescopes, space telescopes, planet surveys, atmospheric studies. The search has expanded across thousands of star systems and thousands of confirmed worlds. The silence has not changed. What makes that silence difficult to explain is that the ingredients for life appear to be everywhere. Carbon is everywhere. Water is everywhere. Oxygen, nitrogen, and organic molecules are scattered throughout the galaxy. We have found planets larger than Earth, smaller than Earth, hotter than lava, colder than Antarctica, worlds wrapped in oceans, worlds wrapped in clouds, and worlds orbiting stars remarkably similar to our own. One distant planet, Kepler 442b, scores as more Earth-like than Mars by several of the metrics scientists use to compare planetary habitability. And yet we have heard nothing. Mars once possessed rivers, lakes, and oceans. Venus may have remained habitable for billions of years before something transformed it into a furnace. Across the galaxy, countless worlds seem to begin with possibility and end in silence. If you're settling in for the night with this one, take a second to like the video. It's a small thing, but it helps more people find their way here. To understand why the universe may be filled with dead worlds, we need to go back to the violent process that creates planets in the first place. A telescope does not see a planet directly. Most of the time, the world itself remains hidden, buried in the glare of its parent star. What we see instead is absence, a tiny reduction in starlight, a faint dip in brightness, a pattern repeating with remarkable precision. That is how many of these distant worlds first reveal themselves to us. When the Kepler Space Telescope began its survey in 2009, it spent years staring at more than 150,000 stars. It watched for minute changes in light, sometimes less than a single percent. If that dimming appeared at regular intervals, astronomers could infer that a planet was passing in front of the star. This technique is called the transit method, a way of detecting worlds through the shadows they cast across immense distances. Later, the Transiting Exoplanet Survey Satellite, better known as TESS, expanded that search across nearly the entire sky. And what emerged was not a universe short on planets, it was overflowing with them. Before Kepler, we could only speculate. After Kepler, planetary systems seemed almost unavoidable. Every region examined appeared to contain worlds, large worlds, small worlds, rocky worlds, gas giants, some circling two stars at once, others orbiting so close to their suns that a year lasted only a few hours. But finding a planet is only the beginning. A dead world is not necessarily a barren rock drifting through darkness. The term covers a much wider range of outcomes. Some worlds never develop the conditions life requires. Others briefly achieve them and then lose everything. A few may host primitive organisms before some planetary catastrophe erases the opportunity entirely. Death on a cosmic scale comes in many forms. We can sometimes glimpse those histories through their atmospheres. As a planet crosses its star, a small fraction of starlight passes through the gases surrounding it before reaching our telescopes. Atmospheric spectroscopy, The study of how matter absorbs specific wavelengths of light allows us to identify the chemical ingredients present there. Oxygen leaves one signature, methane leaves another, water vapor, carbon dioxide, and sulfur compounds each alter the light in recognizable ways. The results have been extraordinary. We have found atmospheres thick with sulfuric acid, worlds wrapped in iron vapor heated beyond imagination, planets where methane dominates the skies, others that may contain oceans of supercritical fluid, a strange state of matter that behaves as both liquid and gas. Chemistry is everywhere, life is not. No confirmed biosignature has survived scrutiny. No unmistakable signal has emerged from the data. This is where the Drake equation enters the story. Proposed by astronomer Frank Drake in 1961, it was never meant to produce a final answer. It was a framework, a way of organizing uncertainty. Each variable represented another step between stars and civilizations. Yet, as observations improved, many of those steps appeared less generous than early estimates suggested, which leaves us facing a difficult possibility. The universe supplied water, carbon, energy, and time to an astonishing number of worlds. But somewhere along the path, almost every one of them appears to have lost the chance to become more. Long before a world can lose its oceans, its atmosphere, or its chance at life, it must first survive its own birth. That sounds straightforward until we look closely at what planetary birth actually involves. There is no calm beginning, no orderly assembly. For roughly 100 million years, a young planetary system resembles a crowded demolition site, governed entirely by gravity. Everything starts with dust. Within a newly formed disk surrounding a star, microscopic grains collide and stick together. Over time, those grains become pebbles. Pebbles become larger bodies called planetesimals, meaning small planetary building blocks. The process accelerates rapidly. Planetesimals crash into one another and merge. Their growing mass strengthens their gravitational pull, drawing in even more material. Soon, objects hundreds of kilometers across begin competing for the same resources. Then the collisions become catastrophic. As these bodies grow into protoplanets, early versions of full sized planets, impact speeds can exceed tens of thousands of kilometers per hour. At those velocities, rock behaves less like stone and more like fluid. Entire surfaces melt, crusts are stripped away, material is blasted into space. Every orbit becomes a crossing path through a crowded battlefield. Our own solar system was no exception. More than 4.5 billion years ago, dozens of Mars sized objects likely occupied the inner solar system. Each followed a slightly different orbit. Each exerted its own gravitational influence. Stability was temporary. Eventually, encounters became unavoidable. Many worlds never made it through this stage. A close gravitational interaction can act like a cosmic slingshot, accelerating a planet until it escapes its star entirely. These exiles become rogue planets, worlds wandering between the stars with no sun to warm them. Recent studies suggest the Milky Way may contain billions of such objects, perhaps even more than the galaxy contains stars. They drift through interstellar space, frozen and isolated, carrying the record of a system they no longer belong to. Survival often comes down to position and timing. A planet that gains enough mass can dominate its orbital neighborhood, clearing away rivals through collisions or ejections. Others endure through a sequence of fortunate gravitational encounters. The difference between permanence and exile may be measured by a handful of close passes occurring at precisely the right moment. Earth's own survival carries the marks of that violence. Around 4.5 billion years ago, a protoplanet known as Theia struck the young Earth. The impact released energy beyond comprehension. Vast portions of both bodies were vaporized. Molten debris expanded outward into orbit before gradually gathering together again. From that wreckage emerged the moon. When you look at it, you are seeing evidence of a planetary catastrophe. But most worlds positioned where Earth formed likely never recovered from their equivalent collision. Some shattered completely, others were thrown away. Before a planet can become habitable, before water settles and atmospheres stabilize, it must first endure this prolonged era of destruction. For countless worlds across the galaxy, the journey ended there. Imagine standing on Earth 4 billion years ago and looking upward. There would be no familiar night sky waiting above you. Instead, the heavens would have been filled with incoming debris, countless fragments of rock and ice tracing deadly paths through the inner solar system. The era of planetary formation had largely passed, yet the violence was far from over. Something had changed between roughly 4.1 and 3.8 billion years ago. The giant planets began shifting positions. As Jupiter and Saturn migrated through the outer solar system, they entered a gravitational resonance, a situation where their orbital periods became linked in a repeating mathematical pattern. That connection amplified their gravitational influence. Small disturbances grew larger, stable orbits unraveled. The result was catastrophic. Vast reservoirs of asteroids and comets were scattered inward. For nearly 300 million years, the inner solar system endured a sustained barrage of impacts. This interval is known as the Late Heavy Bombardment. It was less a storm than a prolonged restructuring of the planetary system itself. Earth sat directly in the path. Some incoming objects measured tens or even hundreds of kilometers across. When bodies of that size strike a planet, the released energy exceeds anything produced by earthquakes, volcanoes, or modern impacts. Entire regions melt, atmospheres are disrupted, oceans can be converted into steam within hours, and it happened repeatedly. Evidence of this era survives on a world that barely changes. The moon lacks weather, flowing water, and active plate tectonics. Its ancient surface preserves a record that Earth erased long ago. The enormous impact basins visible today, including Imbrium and Orientale, formed during this violent chapter. When you look at the moon, you are seeing a surviving archive of events that once affected every rocky planet nearby. For life, the timing could hardly have been worse. If primitive organisms emerged during Earth's earliest hundreds of millions of years, many researchers suspect they were repeatedly eliminated. Conditions may have improved, only to be reset by another impact. Progress, if it existed at all, would have been fragile. Mars endured the bombardment. So did Venus and Mercury. Yet Earth possessed an unusual advantage. Far beyond the orbit of Mars sat Jupiter, containing more than twice the mass of all the other planets combined. Its immense gravity influenced the trajectories of countless objects moving through the solar system. Sometimes Jupiter redirected them outward, sometimes it captured them entirely. In many cases, it prevented future collisions before they could occur. But Jupiter's role was more than protective. By helping clear unstable debris from the system, it contributed to something even more valuable, an ending. Without a giant planet occupying the right region, bombardment can continue for billions of years. A world may experience impact after impact without ever reaching the long stretch of stability that oceans, atmospheres, and biology require. Surveys of exoplanet systems suggest that Jupiter like planets in Jupiter like orbits are far from guaranteed, which means many worlds may never receive the pause that Earth eventually did. If you could place a planet beneath a glass dome and return billions of years later, You might expect its atmosphere to remain waiting where you left it. After all, gases seem weightless, almost permanent. Yet on cosmic timescales, an atmosphere is remarkably fragile. It is less a possession than a negotiation, renewed every day against forces that never stop pushing. Every star wages that pressure campaign. From the surface of a star flows the solar wind, a continuous stream of electrically charged particles moving outward at hundreds of kilometers per second. These particles spread across planetary systems and collide with anything in their path. Over immense spans of time, they chip away at atmospheres molecule by molecule. Planetary scientists call this process atmospheric sputtering, meaning the gradual erosion of a planet's gaseous envelope through energetic particle impacts. The process is relentless. A world may begin with thick skies, abundant clouds, and vast reservoirs of gas. Yet each encounter with the stellar wind removes a tiny fraction, then another fraction, then another. Across millions and billions of years, those losses accumulate. Earth avoids the worst of it. Beneath our feet, thousands of kilometers below the crust, liquid iron circulates through the outer core. That motion generates a magnetic field, an invisible region surrounding the planet. When charged particles arrive from the sun, most are diverted around Earth rather than striking the upper atmosphere directly. You can think of it as a planetary shield, though it is created entirely by physics rather than intention. But maintaining that shield requires extraordinary circumstances. A planet needs sufficient internal heat. It needs a partially molten metallic core. Rotation matters as well. Size plays a role. The balance is delicate, and small differences can alter a world's future completely. Mars offers a striking example. Evidence gathered by orbiters and rovers indicates that Mars once possessed a global magnetic field. Around 4.2 billion years ago, that protective system faded as the planet's interior cooled. Once the magnetic field weakened, the atmosphere became exposed to the solar wind. Losses accelerated. Surface conditions changed. Water became increasingly difficult to sustain. The transformation happened quickly in geological terms. Today, atmospheric pressure on Mars is less than 1% of Earth's. If you stood there without protection, the environment would resemble conditions roughly 35 kilometers above Earth's surface, far above the stratosphere where commercial aircraft travel. The world that once supported rivers became a frozen desert. Mars is not alone. Measurements from missions studying Venus and Mercury reveal similar interactions between stellar particles and atmospheric loss. Beyond our solar system, many rocky exoplanets orbit stars far more active than the Sun. Some endure intense radiation and stronger particle streams for billions of years. What we are discovering is unsettling. Magnetic fields do not appear to be a standard feature of rocky worlds. Many planets likely lose them early. Others may never generate them at all. We often speak about finding planets in habitable zones, yet location is only part of the story. Without a global magnetic shield, an atmosphere exists on borrowed time, and eventually the bill comes due. Today, Mars looks almost frozen in time. Dust moves across vast plains. Thin clouds drift through a pale sky. Temperatures plunge far below anything most life on Earth could tolerate. If you arrived there knowing nothing of its past, you might assume it had always been this way. The evidence tells a different story. As orbiters mapped the Martian surface in increasing detail, they began revealing patterns that should not exist on a permanently frozen world. Valleys branch like river systems. Sediment layers lie stacked inside ancient basins. Delta formations spread outward where flowing water once entered standing lakes. These features point toward a very different Mars, one that existed between roughly 4 billion and 3.5 billion years ago. Back then, the planet appears to have possessed many ingredients we associate with habitability. Its atmosphere was thicker, surface pressure was higher, a global magnetic field surrounded the planet, water flowed across the landscape, collecting in lakes and perhaps even seas. Beneath the surface, hydrothermal systems, regions where water interacts with heat from the interior, may have created environments suitable for microbial organisms. The rovers, Curiosity and Perseverance, have strengthened that picture. Both machines have examined rocks shaped by ancient water. They have identified mineral deposits that form only in wet conditions. Mudstones, lake sediments, and chemically altered minerals all point toward a world that remained habitable for extended periods. We are no longer asking whether liquid water existed there. We know it did. One of the most striking discoveries involves a vast northern body of water, often called Oceanus Borealis, or the Paleo-Ocean. Reconstructions suggest this ocean may have covered roughly 19% of the planet's surface. In some regions, depths likely exceeded 1.5 kilometers. Imagine standing on an ancient Martian shoreline and looking toward a distant horizon of open water. That possibility is supported by growing geological evidence. Yet none of it survived. The chain of events appears to have begun deep inside the planet. Mars is only about half the diameter of Earth. Smaller worlds lose internal heat more rapidly because they contain less material to retain energy over long periods. As the Martian interior cooled, the mechanism generating its magnetic field weakened and eventually failed. That change altered everything. Without magnetic protection, charged particles from the sun gained increasing access to the upper atmosphere. Atmospheric gases escaped into space. Pressure declined. Liquid water became unstable at the surface. Reservoirs evaporated, froze, or gradually vanished. Temperatures fell. Conditions that may once have supported life narrowed and then disappeared. Remarkably, this transformation may have unfolded within only a few 100 million years, an eye blink in planetary history. Mars matters because it provides more than a cautionary example. It reveals a common vulnerability. Many rocky planets, discovered around other stars, occupy a similar size range. If they cool as Mars cooled, their habitability may also be temporary. When we look at the red planet today, we may be seeing the most common fate awaiting worlds that once seemed full of promise. Among all the worlds in our solar system, Venus presents perhaps the most unsettling possibility. Mars appears to have lost a chance at habitability early. Venus may have held on to that chance for an extraordinarily long time. When we study its history, we are not looking at a world that failed immediately. We are looking at one that may have come remarkably close to success. For much of the 20th century, Venus was difficult to imagine as anything other than hostile. Thick clouds concealed its surface. Temperatures crushed spacecraft. Atmospheric pressure overwhelmed engineering limits. Yet as climate modeling improved during the 1980s and 1990s, a surprising idea began to emerge. Ancient Venus may have been temperate. Researchers found growing evidence that conditions billions of years ago could have been dramatically different from those we observe today. Some models suggested the presence of liquid water oceans. Others indicated stable temperatures capable of supporting long-term surface water. Instead of an inferno, early Venus may have resembled a humid, ocean-bearing world orbiting closer to the Sunday. The possibility became even more intriguing in 2016. A study conducted by scientists at NASA used advanced climate simulations to reconstruct ancient Venus under different conditions. Assuming a slower rotation rate and substantial surface water, The results suggested habitable environments could have persisted for as long as 2 billion years. Consider what that means. On Earth, multicellular life emerged within a shorter span of time. Venus may have had enough time. But planetary histories do not always move gradually. Sometimes they cross a threshold. At some point, likely before roughly 700 million years ago, Venus experienced enormous volcanic activity. Vast quantities of carbon dioxide poured into the atmosphere. Some researchers suspect a global resurfacing event, a period when large portions of the planet were reshaped by volcanic processes. Whatever the precise trigger, the atmosphere began changing rapidly. Then, a dangerous feedback loop took hold. Carbon dioxide traps heat. Higher temperatures release additional carbon dioxide from rocks and surface reservoirs. More carbon dioxide increases warming further. The cycle reinforces itself. Each step strengthens the next. Planetary scientists call this a runaway greenhouse effect, a process in which warming becomes self-amplifying and increasingly difficult to stop. Once fully established, recovery becomes extraordinarily unlikely. Today, Venus records surface temperatures around 465 degrees Celsius. That is hot enough to melt lead. Atmospheric pressure reaches approximately 92 times that of Earth. Standing on the surface would expose you to pressures comparable to conditions roughly 900 meters beneath Earth's oceans. Yet Venus remains strikingly familiar in one respect. Its size closely matches Earth's. Its mass is similar. Its composition shares important characteristics. With our own planet, the differences that separate paradise from catastrophe appear surprisingly small. A shift in atmospheric chemistry, a prolonged episode of volcanism, a slightly different balance between incoming sunlight and greenhouse warming. That realization extends far beyond Venus itself. Many rocky planets orbit stars at distances where similar transitions may occur. Some may drift just far enough toward instability for the process to begin. Others may carry internal heat budgets that drive excessive volcanism. Across the galaxy, worlds can spend ages appearing promising, only to cross a line from which there is no return. If you were designing a galaxy for life, red dwarf stars would seem like an excellent place to start. They are small, stable, and astonishingly long-lived. While stars like our Sun survive for billions of years, many red dwarfs are expected to burn for trillions. Some will still shine long after every sun-like star in the Milky Way has faded away. At first glance, they appear almost ideal. Astronomers classify these objects as M dwarfs, the smallest and coolest category of ordinary stars. They dominate the galaxy. Between 70 and 75% of all stars in the Milky Way belong to this group. When we count potential homes for life, most of the available real estate exists around red dwarfs, and many of them host planets. Observations over the last 2 decades have revealed rocky worlds orbiting these stars in remarkable numbers. One of the most famous systems is TRAPPIST-1, located about 40 light-years from Earth. There, 7 rocky planets circle a single red dwarf. 3 occupy the star's habitable zone, the region where temperatures may allow liquid water to exist at the surface. It sounds encouraging, but appearances can be deceptive. Young red dwarfs are far more active than their modest size suggests. During their early history, they unleash powerful eruptions called superflares. A superflare is an enormous release of magnetic energy that floods surrounding space with radiation. Some of these events exceed the strongest solar flares ever recorded from our Sun by orders of magnitude. Nearby planets take the full impact. Ultraviolet radiation, high-energy X-rays, and streams of charged particles repeatedly strike their atmospheres. A single flare may do little lasting damage. Thousands of them, over millions or billions of years, tell a different story. Atmospheric gases can be stripped away, surface chemistry can be altered. Biological molecules may struggle to survive long enough to establish anything complex. Distance creates another challenge. Because red dwarfs are relatively dim, their habitable zones lie very close to the star. A planet must orbit nearby to receive enough warmth. Yet close orbits produce a phenomenon called tidal locking, where one side of a world permanently faces its star while the opposite side remains turned away. The same process keeps one face of Earth's moon directed toward us. Many red dwarf planets may share that fate. One hemisphere experiences endless daylight, the other endures perpetual darkness. Climate models suggest that extreme temperature contrasts could develop unless a sufficiently thick atmosphere redistributes heat. Some worlds may avoid the worst outcomes, others may not. Research published in 2017 examined the activity of TRAPPIST-1 and found flare levels capable of removing an Earth-like atmosphere within only a few million years under certain conditions. Yet the difficulties extend beyond atmospheric loss. Some scientists argue that red dwarfs produce too little of a specific range of ultraviolet radiation needed for chemical reactions linked to life's origin. Taken together, these findings lead to an uncomfortable possibility. The galaxy's most abundant stars may also be among its least welcoming. If that conclusion proves correct, then a vast fraction of all rocky planets in the Milky Way may never have had a realistic chance to become living worlds. When we picture a habitable world, we usually imagine a planet circling the right kind of star at the right distance. That picture feels complete until we step back and widen the scale. A planet exists inside a star system, but that star system exists inside a galaxy. The larger environment matters too. Sometimes it matters enormously. Astronomers use the term galactic habitable zone to describe regions of a galaxy where conditions may allow complex life to emerge and persist. It is a broader version of the familiar habitable zone around a star. Instead of measuring planetary distance from sunlight, we measure a star system's position within the Milky Way itself. The result is surprisingly restrictive. Near the galactic center, stars crowd together in extraordinary numbers. Distances between neighboring stars shrink dramatically compared to our region of space. At first, that density might seem beneficial. More stars could mean more planets. More planets could mean more opportunities for life. But crowded neighborhoods come with hazards. Massive stars are more common there. Supernova explosions occur more frequently. Gamma-ray bursts, intense beams of high-energy radiation produced by extreme cosmic events, become a greater threat. Gravitational interactions between nearby stars can disturb planetary orbits over long timescales. A stable planetary system becomes much harder to maintain. The inner galaxy is rich in possibilities, yet poor in safety. Moving outward creates a different problem. Beyond the main disk of the Milky Way, the abundance of heavy elements begins to decline. Astronomers call this metallicity, the concentration of elements heavier than hydrogen and helium. Those elements are essential for building rocky planets, complex chemistry, and the geological diversity associated with habitable worlds. Without sufficient metallicity, there is less raw material available. Planet formation still occurs, but constructing Earth-sized rocky worlds becomes increasingly difficult. The ingredients simply become scarcer. Between these extremes lies a narrow compromise. Current estimates place the galactic habitable zone roughly between 23,000 and 30,000 light years from the Milky Way's center. Earth resides almost directly within that range. Our solar system sits approximately 26,000 light years from the galactic core, positioned in a region that balances chemical richness with long term stability. Even there, dangers remain. The Milky Way's spiral arms are active regions of star formation. New stars are born there in large numbers. Massive stars live brief lives before ending in spectacular explosions. Increased star formation therefore means increased radiation hazards and greater gravitational disruption. By coincidence or fortune, our solar system currently orbits between major spiral arms rather than inside one. Location continues to matter at every scale. Consider globular clusters, dense collections containing hundreds of thousands of stars, packed into relatively small volumes. Their crowded conditions create unstable orbital environments, while their low metallicity limits planet formation. Many researchers suspect they are poor candidates for complex life. The same concern extends to entire galaxy types. Elliptical galaxies tend to contain older stellar populations and reduced heavy element abundance. Only large spiral galaxies resembling the Milky Way appear to provide the right balance, and even within those galaxies, only certain regions qualify. The farther we zoom out, the smaller the map of possibility becomes. Some stars spend millions of years building themselves toward a final moment. Deep within their cores, heavier and heavier elements accumulate as nuclear fusion continues. Eventually, the balance fails. Gravity wins. In less time than it takes to read a sentence, a star that may have existed for millions of years reaches its end. Then the explosion arrives. A supernova is the death of a massive star, and it ranks among the most energetic events in the observable universe. During those final moments, a single star can release more energy than our sun will produce throughout its entire 10 billion year lifetime. For a brief period, one exploding star may outshine an entire galaxy. Beauty is only part of the story. A supernova does not merely illuminate space, it transforms it. Expanding shock waves race outward. High energy particles flood surrounding regions. Powerful bursts of radiation sweep through nearby planetary systems. Any world, unfortunate enough to be close, becomes part of the event, whether it wants to or not. Distance determines survival. Current estimates suggest that a supernova occurring within roughly 25 to 30 light years of Earth could significantly damage the ozone layer, the atmospheric region that absorbs much of the sun's harmful ultraviolet radiation. With that protection weakened, surface ecosystems would face dramatically increased exposure. Move the explosion closer, within approximately 10 light years, and the consequences become far more severe. At that range, extinction becomes a realistic outcome. Earth may have experienced something related to this danger before. Around 445 million years ago, the Ordovician mass extinction eliminated roughly 85% of marine species. Several hypotheses have been proposed to explain the event. Among them is the possibility of a nearby gamma ray burst, an intense beam of radiation associated with some of the most extreme cosmic phenomena. The evidence remains debated, yet the idea highlights a broader reality. Life does not exist in isolation from astronomical events. A thriving biosphere can be altered by something occurring dozens or even hundreds of light years away. The early universe faced this problem constantly. Massive stars formed more frequently during the first few billion years of cosmic history. They consumed their fuel rapidly, and exploded after relatively short lives. As a result, supernovae occurred far more often than they do today. The young Milky Way was filled with regions where repeated stellar deaths continually reshaped the environment. Long-term habitability would have been difficult to maintain. Even in the present era, potential future supernova candidates attract scientific attention. One example is the star system Ik Pegasi, located approximately 150 light-years away. Astronomers believe it may eventually produce a supernova. Another famous candidate is Betelgeuse, the red supergiant visible in the constellation Orion. It is expected to explode within the next 100,000 years, close enough to create a spectacular sight in Earth's sky, yet distant enough to pose little danger. But many worlds are not so fortunate. Stars tend to form in clusters and stellar nurseries. These regions produce generations of massive stars alongside smaller ones. A planet born there may spend its entire existence surrounded by future supernovae. Complex life requires time. In many corners of the galaxy, time is precisely what repeated stellar explosions refuse to provide. The next threat did not arrive from space. No asteroid crossed the sky. No nearby star exploded. This time, the danger emerged from the biosphere itself. It began with organisms so small that trillions could fit within a single drop of water, yet their collective influence would alter the destiny of an entire planet. Around 2.4 billion years ago, Earth entered one of the strangest episodes in its history. At that time, the atmosphere looked nothing like the one you breathe today. Free oxygen was almost absent. Instead, the air contained large amounts of methane, nitrogen, and carbon dioxide. For more than a billion years, life had adapted to those conditions. Entire ecosystems depended on a world without oxygen. Then evolution produced something new. Cyanobacteria, microscopic organisms capable of photosynthesis, developed a remarkable ability. Using sunlight as an energy source, they split water molecules and released oxygen as a waste product. At first, the change seemed insignificant. Oceans and rocks absorbed much of the oxygen being produced. Chemical reactions removed it almost as quickly as it appeared. But biology kept working. Generation after generation, cyanobacteria multiplied across shallow seas. Their populations expanded. Oxygen production increased. Eventually, the natural sinks became saturated. For the first time, oxygen began accumulating in the atmosphere. That transformation proved catastrophic for much of Earth's existing life. To modern organisms, oxygen is essential. To many early microbes, it was poison. Oxygen readily reacts with biological molecules, damaging cellular machinery that evolved in its absence. Entire groups of anaerobic organisms, life forms that survive without oxygen, suddenly found themselves living in an increasingly hostile environment. The planet was changing from within. A second consequence followed close behind. Atmospheric methane had been one of Earth's most effective greenhouse gases. As oxygen concentrations rose, oxygen reacted with methane and removed it from the atmosphere. The insulating effect weakened, temperatures dropped, global cooling intensified. The result may have been extraordinary. Geological evidence suggests Earth entered a severe glaciation episode often associated with Snowball Earth conditions, where ice expanded across vast portions of the planet. Some models indicate freezing may have extended from the poles toward equatorial regions. A world once dominated by microbial ecosystems became far colder and far less stable. Scientists call this transition the Great Oxidation Event. It remains one of the closest examples of a biologically driven planetary crisis. Life altered the atmosphere. The altered atmosphere transformed the climate. The transformed climate threatened much of the life that had created the change in the first place. Recovery was slow. Hundreds of millions of years passed before oxygen tolerant organisms diversified and ecosystems adjusted to the new reality. Yet the deeper lesson extends far beyond Earth. The emergence of life is not necessarily the end of a world's difficulties. In some cases, life may create new dangers before complex organisms ever appear. That possibility carries an unsettling implication for the broader galaxy. A microbial biosphere could transform its environment into something hostile long before intelligence evolves. From across interstellar distances, we might never recognize what happened. A world that poisoned itself through its own metabolism could appear chemically ordinary, leaving almost no obvious trace of the drama that unfolded there. There have been moments in Earth's history when standing at the equator would have offered little comfort. No tropical seas, no warm coastlines, no refuge in lower latitudes. For long stretches of time, the distinction between pole and tropics may have nearly vanished beneath a world wrapped in ice. This was Snowball Earth. Between roughly 720 million and 635 million years ago, our planet experienced some of the most severe glaciations known to science. Geological evidence from multiple continents suggests that ice sheets expanded far beyond polar regions. Glacial deposits appear in rocks that formed near the equator, implying that frozen conditions reached places that today receive intense sunlight throughout the year. Temperatures fell dramatically. Some climate models estimate global averages approaching negative 50 degrees Celsius. Oceans developed thick surface ice. Continents disappeared beneath vast frozen expanses. From orbit, Earth may have appeared less like a blue world and more like a pale sphere reflecting sunlight back into space. And it may have happened more than once. Researchers have identified at least two major Snowball Earth episodes, known as the Sturtian and Marinoan glaciations. Evidence for additional events remains under investigation. Each episode persisted for millions of years, making them among the longest climate crises our planet has ever endured. The mechanism behind their severity is deceptively simple. Scientists call it the ice albedo feedback. Albedo refers to a surface's ability to reflect sunlight. Ice reflects far more solar energy than water or rock. As ice spreads, more sunlight is reflected away from the planet. Reduced absorption leads to further cooling. Cooling creates additional ice. The cycle reinforces itself with each step. Once established, the process becomes extraordinarily difficult to stop. The planet effectively locks itself into a frozen state. Sunlight alone may be insufficient to reverse the trend. Yet deep beneath the ice, another process continued. Volcanoes did not stop erupting. Carbon dioxide continued entering the atmosphere through volcanic outgassing, the release of gases from Earth's interior. Year after year, the gas accumulated. Then century after century, then millions of years more. Because weathering processes were suppressed beneath widespread ice cover, little carbon dioxide was removed from the atmosphere. Concentrations gradually rose until the greenhouse effect became overwhelming. Heat began accumulating faster than it could escape. Eventually, the frozen equilibrium collapsed. The thaw was dramatic. A planet locked in ice swung rapidly toward greenhouse conditions. Oceans melted, weather patterns transformed, chemical cycles reorganized. The transition itself may have driven substantial ecological disruption, creating new extinction pressures even as habitability returned. Yet, something remarkable followed. The appearance of complex multicellular life occurred after the final Snowball Earth episodes ended. Scientists continue debating the connection, but some researchers suspect these glaciations acted as both obstacle and catalyst. They eliminated vulnerable ecosystems while reshaping environments in ways that encouraged evolutionary innovation. That possibility extends beyond Earth. A rocky planet entering a similar frozen state may not always escape. Without sufficient volcanism, favorable continental arrangements, or the right atmospheric conditions, global ice could persist indefinitely. Several known exoplanets may exist in such conditions today, carrying hidden oceans beneath frozen surfaces, separated from the wider cosmos by kilometers of ancient ice. From space, continents appear permanent, coastlines seem fixed, mountain ranges look ancient and immovable. Yet beneath that appearance, Earth's surface is constantly rearranging itself. Entire sections of crust drift, collide, sink, and rise again. The ground beneath every forest, desert, and ocean is participating in a process so gradual that you never notice it, yet so important that complex life may depend on it. This process is plate tectonics. Plate tectonics describes the movement of large sections of Earth's outer shell across the planet's surface. These plates float atop hotter, slowly moving material deeper within the mantle. Their motion creates mountains, opens oceans, triggers earthquakes, and fuels volcanism. But geology is only part of the story. The climate depends on it too. One of Earth's most important systems is the carbon silicate cycle, a long-term planetary recycling mechanism. Carbon dioxide enters the atmosphere through volcanic activity. Rain and weathering gradually pull some of that carbon dioxide back out by reacting with rocks. Rivers transport the resulting materials into the oceans. Over immense timescales, portions of the seafloor sink beneath continental plates and carry that carbon back into Earth's interior. Then the cycle begins again. Volcanoes eventually release part of that stored carbon dioxide back into the atmosphere. The result is a self-adjusting system that operates over millions of years. Too much atmospheric carbon dioxide increases weathering rates. Too little reduces them. The process functions as a planetary thermostat. Its influence has been extraordinary. Since the Sun formed, its luminosity has increased by roughly 30%. A brighter star should have pushed Earth toward progressively warmer conditions, yet liquid water has persisted for billions of years. Plate tectonics helped maintain that balance by regulating atmospheric carbon dioxide over geological timescales. But remove tectonics and the equation changes. Without crustal recycling, carbon dioxide can accumulate in the atmosphere without an efficient long-term return path. Greenhouse warming strengthens. Climate stability becomes harder to maintain. A planet loses one of its most important correction mechanisms. Venus may provide an example. Evidence suggests that Venus once possessed tectonic activity early in its history. Today, however, it appears largely absent. Many planetary scientists believe the loss of tectonic recycling contributed directly to the extreme greenhouse conditions that followed. Mars represents a different outcome. It never developed large-scale plate tectonics comparable to Earth's. Its crust remained largely fixed while its internal heat gradually dissipated. Neither path led to long-term habitability. What determines whether a planet develops tectonics remains an active area of research. Size matters. Internal temperature matters. Water stored within the mantle appears important. Crust composition influences behavior as well. Multiple factors must align simultaneously. That combination may be uncommon. Research, published in 2014, suggested that many rocky exoplanets could belong to a category known as stagnant lid planets. A stagnant lid planet possesses a rigid outer shell that does not break into mobile plates. Without movement, atmospheric recycling slows dramatically. Surface chemistry becomes less dynamic. Long-term climate regulation weakens. When we consider Earth's history, tectonics often feels ordinary because it surrounds us. Yet the more we learn about other worlds, the more unusual it appears. Our moving crust may not be a standard planetary feature. It may be one of the rare conditions that allowed a living world to remain alive. Every month, the moon drifts around Earth with such regularity that it can feel almost decorative, a familiar companion crossing the night sky exactly as expected. Yet, if we removed it entirely and watched Earth's future unfold over millions of years, the planet beneath your feet would become far less predictable. The change would begin with a tilt. Earth rotates on an axis inclined by roughly 23.5 degrees relative to its orbit around the Sunday. That tilt creates the seasons. Summer, winter, spring, and autumn all emerge from this simple geometric arrangement. More importantly, the tilt has remained remarkably stable across immense stretches of time. That stability is not guaranteed. The moon exerts a continuous gravitational influence on Earth, acting as a stabilizing weight on our planet's rotational behavior. You can think of it as a long-term regulator, helping prevent extreme variations in the angle at which Earth presents itself to the Sunday. Without that influence, the story changes dramatically. Computer simulations conducted during the 1990s suggested that Earth's axial tilt could wander chaotically over millions of years if the moon did not exist. Instead of remaining near its current value, the tilt might fluctuate anywhere between 0 degrees and 85 degrees. Those numbers carry enormous consequences. At 0 degrees, seasonal variation would nearly disappear. At 85 degrees, entire climate systems would be transformed. The poles could receive more annual solar energy than equatorial regions. Weather patterns would reorganize. Ice sheets would advance and retreat unpredictably. Ecosystems would struggle to adapt to constantly shifting conditions. Complex life depends on stability. Not perfect stability, but enough consistency for evolutionary processes to operate across vast timescales. The moon helps provide that consistency. It reduces the likelihood of extreme axial swings that could repeatedly reset planetary environments before biological complexity gains a foothold. We can see hints of this elsewhere. Mars lacks a large stabilizing moon. As a result, its axial tilt has varied substantially throughout its history. Studies suggest shifts between roughly 15 and 35 degrees during the past 5 million years alone, with evidence indicating even greater variations farther back in time. Martian climates have repeatedly transformed as a consequence. Earth largely avoided that fate. The remarkable part is how our moon formed in the first place. Current models indicate it originated after the colossal impact that created the debris field discussed earlier. A Mars-sized body known as Theia collided with the young Earth approximately 4.5 billion years ago. Material blasted into orbit, gradually merged into a single large satellite. A violent accident became a long-term safeguard. Its influence extends beyond axial stability. Lunar gravity generates tides, creating rhythmic movements between land and sea. Many researchers believe Tidal environments played an important role in the transition of life from aquatic habitats toward terrestrial ecosystems. Shorelines repeatedly flooded and retreated, creating dynamic chemical environments where evolutionary experimentation could occur. But large moons of this scale may be uncommon. Many rocky planets likely orbit their stars alone or with much smaller companions. If so, countless worlds may experience chaotic shifts in climate that Earth never faced. What appears above us each night may therefore be more than a companion. It may be one of the reasons complex life had enough time to endure. Imagine arriving on Earth shortly after its formation and measuring the sunlight reaching the surface. The numbers would present a problem immediately. The young sun was far dimmer than the star we know today. By every straightforward calculation, our planet should have been locked beneath global ice. Yet the rocks tell a different story. Tiny zircon crystals discovered in Western Australia preserve evidence that liquid water existed on Earth's surface roughly 4.4 billion years ago. That places oceans astonishingly early in the planet's history, only about 200 million years after Earth itself formed. Water was present, rivers and seas were possible. Somehow, a world orbiting a weaker star avoided becoming a frozen wasteland. This contradiction has a name. In 1972, astronomers Carl Sagan and George Mullen formally described what became known as the faint young sun paradox. A paradox is a situation where observations and predictions appear incompatible. The young sun produced only about 70% of its current luminosity, meaning its total energy output was significantly lower than today. The mathematics seemed clear. A weaker sun should have delivered too little energy to maintain widespread liquid water. Average temperatures ought to have remained below freezing across much of the planet. Instead, geological evidence consistently points toward a world where water flowed and oceans persisted. Something compensated for the missing heat. The leading explanation involves Earth's early atmosphere. Scientists believe concentrations of greenhouse gases were substantially higher than they are today. Carbon dioxide and methane trapped outgoing heat, strengthening the greenhouse effect and preventing global freezing. These gases acted like an insulating blanket, retaining enough warmth to keep water in its liquid state. But the margin for error was remarkably small. Too little greenhouse warming and Earth freezes. Too much greenhouse warming and temperatures rise uncontrollably. Maintaining habitability required a balance that shifted continually as the sun slowly brightened over billions of years. Earth somehow managed it. As solar luminosity increased, geological and atmospheric processes adjusted, carbon dioxide levels changed, weathering rates evolved, volcanic activity contributed. Multiple systems interacted across immense timescales, helping maintain conditions suitable for liquid water despite an ever-changing energy input from the sunday. Other worlds faced the same challenge. Mars once possessed rivers, lakes, and perhaps even northern oceans. Evidence gathered by orbiters and rovers confirms that liquid water existed there billions of years ago. Yet by roughly 3.5 billion years ago, much of that evidence begins to disappear. The planet could not sustain the atmospheric conditions needed to solve its own version of the paradox. Its climate stability failed. What makes Earth's history remarkable is not that it started with liquid water, it is that liquid water endured. Across billions of years, the sun became steadily brighter while Earth's atmosphere repeatedly adjusted. The balance never drifted far enough toward permanent freezing or irreversible overheating. That outcome may be far less common than it appears. Any rocky planet orbiting a young star faces the same fundamental challenge. A habitable zone alone is not enough. The atmosphere must respond correctly as stellar conditions evolve. Many worlds may begin with the potential for oceans. Far fewer may possess the chemistry required to keep them. Consider the journey from a newly formed planet to a civilization capable of crossing interstellar space. At first, it seems like a sequence of gradual improvements. A planet forms, life appears, complexity grows, intelligence emerges, technology follows. Given enough time, the process feels almost inevitable. Yet the universe does not look inevitable. Despite hundreds of billions of stars in the Milky Way and vast numbers of potentially habitable worlds, we see no clear evidence of civilizations spreading across the galaxy. This contradiction sits at the heart of the Fermi Paradox, and in 1998, economist Robin Hanson proposed one of its most influential explanations. He called it the Great Filter. The idea is deceptively simple. Somewhere between a lifeless planet and a civilization capable of expanding through the stars lies at least one step so difficult that almost no world successfully completes it. The filter could be a biological obstacle, it could be a technological one, it could even be several obstacles acting together. The challenge is that we do not know where it lies. If the filter is behind us, then humanity has already passed the hardest barrier. Perhaps the origin of life was extraordinarily rare. Perhaps complex cells almost never emerge. In that case, our existence would represent an exceptional outcome, and the galaxy might truly contain very few technological civilizations. That possibility is comforting in one sense. But there is another possibility. If the filter lies ahead, then civilizations may routinely reach a certain stage before disappearing. They might develop technology and then collapse. They might alter their planets beyond recovery. They might encounter limits we have not yet imagined. Under that scenario, the galaxy remains empty because almost nobody survives long enough to cross the final threshold. To understand the idea, we can trace the proposed filters in order. The first candidate is abiogenesis, the origin of life from non-living chemistry. Despite decades of research, scientists have never recreated the complete transition from chemistry to biology. Perhaps it is common. Perhaps it is extraordinarily rare. Next comes the emergence of the eukaryotic cell, a complex cell containing a nucleus and specialized structures. On Earth, this transition required roughly 1.5 billion years. It may have happened only once. Additional candidates follow. Sexual reproduction dramatically increased genetic diversity. Multicellular life introduced new levels of biological organization. Nervous systems enabled complex behavior. Intelligence allowed abstract thought. Technology transformed intelligence into a planetary force. Each step narrowed the path. Then comes another leap. A technological species must survive long enough to become an interstellar one. Knowledge alone is insufficient. Stability matters. Longevity matters. A civilization must avoid destroying itself while developing the capacity to move beyond its home world. Every stage appears plausible when viewed individually. Together, they form an astonishing chain of requirements. The Great Filter asks a simple question that remains unanswered. Which of those steps is truly rare? At present, we cannot tell. We possess only one example of a living world, one evolutionary history, and one technological species. From a scientific perspective, a sample size of one leaves almost everything uncertain. Every living thing you have ever seen belongs to a chain of ancestry stretching back to a single beginning. Plants, animals, fungi, bacteria, and every organism that has ever existed on Earth ultimately trace their history to one moment when non living chemistry became something more. That moment remains unknown. Scientists often describe the origin of life as one of the greatest unanswered questions in biology. Yet, it is important to understand what kind of mystery this is. We are not dealing with a missing detail. We are standing at the edge of a frontier where the central event itself has never been observed, reproduced, or fully explained. We know many of the ingredients. Early Earth possessed liquid water. Energy sources were abundant, including sunlight, lightning, geothermal heat, and chemical reactions occurring deep within the planet. Amino acids, the molecular components of proteins, can form naturally under suitable conditions. Nucleotides, the building blocks of genetic material, also appear capable of emerging through ordinary chemistry. The pieces existed. A famous demonstration came in 1952 when Stanley Miller and Harold Urey conducted an experiment designed to simulate conditions on the young Earth. By introducing electrical sparks into a mixture of simple gases, they produced amino acids without any biological intervention. The result showed that some of life's fundamental ingredients arise surprisingly easily. But ingredients are not life. Amino acids are not cells. Nucleotides are not organisms. Between a collection of molecules and a living system lies an immense conceptual gap. Somewhere along that path, chemistry crossed a threshold and became biology. That transition remains elusive. One leading proposal is the RNA world hypothesis. RNA, ribonucleic acid, is a molecule capable of storing information and performing certain chemical functions. Some researchers suggest that self-replicating RNA existed before modern DNA and proteins evolved. In this scenario, RNA served as an intermediate stage between chemistry and life. The idea is compelling. Yet, even if self-replicating RNA molecules existed, we still face additional questions. How did those molecules organize into cells? How did metabolism emerge? How did genetic information become stable enough to persist across generations? No complete pathway has yet been demonstrated. What makes the puzzle even stranger is timing. Evidence suggests that life appeared on Earth remarkably early. Depending on how the data are interpreted, living organisms may have emerged within 500 million years of the planet becoming habitable, perhaps even within 200 million years. On geological timescales, that is astonishingly fast. Two possibilities follow. Abiogenesis, the origin of life from non-living matter, may be relatively easy when conditions are suitable. If so, life should be widespread throughout the cosmos. But there is another possibility. Earth may have experienced an extraordinarily improbable event that happened quickly once and has never happened again nearby. At present, we cannot distinguish between those explanations. Everything depends on finding a second example. It could be beneath the ice of an ocean moon. It could exist beneath the surface of Mars. It could emerge from the atmosphere of a distant exoplanet. Even a microbial biosphere would transform our understanding overnight. Until then, the absence of evidence remains meaningful. Every year that passes without discovering another origin of life adds another piece of information to the mystery itself. If you compressed Earth's history into a single day, one of the strangest chapters would be the longest. Life appeared relatively early. The planet became inhabited. Microorganisms spread across oceans and coastlines. Then, for an immense span of time, almost nothing changed in ways that would be recognizable to us. The world remained microbial. For roughly 1.5 to 2 billion years after life emerged, prokaryotes dominated the biosphere. A prokaryote is a simple cell lacking a nucleus, the compartment that stores genetic material in more complex organisms. These cells were extraordinarily successful. They colonized oceans, sediments, and virtually every environment available to them. Yet, complexity advanced very slowly. There were no forests, no animals, no eyes, no nervous systems, no predators chasing prey through ancient seas. Earth was alive, but it remained a planet of microscopic organisms carrying out variations of the same basic biological strategies. Then something unusual happened. At some point between roughly 2 billion and 1.5 billion years ago, a cell engulfed another cell. Such encounters were probably common. Cells consume other cells constantly. The remarkable part is what happened next. Digestion never occurred. Instead of being broken down, the engulfed bacterium survived within its host. Over time, the relationship deepened. The smaller cell provided energy, the larger cell provided protection and resources. What began as an accident evolved into a permanent partnership. This process is called endosymbiosis. Endosymbiosis means one organism living inside another in a mutually beneficial arrangement. The engulfed bacterium eventually became the mitochondrion, a specialized structure responsible for generating energy inside complex cells. Today, mitochondria exist in virtually every animal, plant, and fungal cell on Earth. You carry them right now. Every breath you take relies on descendants of that ancient partnership. Every movement, thought, and heartbeat depends on mitochondria, converting chemical energy into forms usable by your cells. Their presence links modern life to a single evolutionary event billions of years in the past. What makes the story even more remarkable is its apparent uniqueness. All known complex organisms descend from a common ancestor possessing mitochondria. Evidence suggests that endosymbiosis may have occurred only once in Earth's history. One successful merger between two microscopic organisms became the foundation for every complex ecosystem that followed. Without it, the planet would look very different. Bacteria would still thrive, microbial communities would still cover oceans and rocks, life would exist, but multicellular organisms, large bodies, and eventually intelligence might never have appeared. The timescale itself offers an important clue. If the transition from simple cells to complex cells required nearly 2 billion years on a life-bearing planet, perhaps the step is genuinely difficult. Other worlds may have crossed the threshold from chemistry to biology, yet stalled indefinitely at the microbial stage. That possibility changes how we think about inhabited planets. A world covered in bacteria is technically alive, yet, from interstellar distances, detecting that life would be extraordinarily difficult. Observationally, a microbial biosphere and a sterile planet may appear almost identical. The universe could contain countless living worlds that never progressed beyond their first successful cells, hidden in plain sight behind the limits of our instruments. Long before forests, insects, reptiles, or mammals appeared, Earth spent billions of years exploring far simpler possibilities. Microbial communities spread across coastlines and shallow seas. Soft-bodied organisms emerged later, adding new forms without fundamentally changing the pace of evolution. Life existed everywhere, conditions allowed, yet complexity advanced slowly, almost cautiously, across immense stretches of geological time. Then the pattern broke. Around 538 million years ago, the fossil record began recording something extraordinary. Within roughly 20 million years, a brief interval by geological standards, an astonishing variety of animal forms appeared. Organisms developed limbs, shells, spines, compound eyes, jaws, and entirely new ways of moving through their environments. The change was dramatic. Paleontologists call this interval the Cambrian explosion. The name does not imply a single instant, but rather a sustained burst of evolutionary innovation compressed into a comparatively short period. When we examine rocks from before and after this transition, the contrast is striking. A world dominated by relatively simple organisms gave way to ecosystems crowded with experimentation. What triggered such a transformation remains one of biology's enduring questions. One leading explanation involves oxygen. Atmospheric oxygen levels appear to have risen significantly before the Cambrian period. Larger bodies require greater energy production, and oxygen enables highly efficient metabolism. A richer oxygen supply may have allowed organisms to grow larger, move faster, and support increasingly complex tissues. But oxygen alone may not explain everything. Another possibility centers on vision. Eyes evolved in several early animal groups, introducing a revolutionary new ecological pressure. Once organisms could detect predators at a distance, survival strategies changed. Armor became valuable, camouflage mattered, speed offered advantages. Predators improved, prey adapted, and evolution accelerated through an escalating competition that transformed entire ecosystems. Other factors may have contributed as well. Changes in ocean chemistry could have provided new biological opportunities. Nutrients may have circulated differently through ancient seas. Recovery from the final Snowball Earth episodes may also have opened ecological space for diversification. Several mechanisms may have converged at precisely the right moment. Evidence of this remarkable era survives in one of the most important fossil sites ever discovered. The Burgess Shale of British Columbia preserves creatures unlike anything alive today. Some possessed 5 eyes, others carried rows of grasping appendages. Certain species displayed circular mouths lined with sharp structures resembling teeth. Many forms appear so unfamiliar that early researchers struggled to determine how they were related to modern animals. Most disappeared. These organisms represent evolution's abandoned pathways, experiments that flourished briefly before vanishing. Only a fraction of Cambrian lineages left descendants that survived into later ages. The diversity we see today emerged from a much larger field of possibilities. That detail carries important implications when we think beyond Earth. If the Cambrian explosion required a rare combination of oxygen levels, environmental pressures, ecological interactions, and geological timing, then complex life may depend on far more than the mere presence of living cells. Across the galaxy, countless worlds could harbor microbial ecosystems while never crossing the threshold that transformed Earth from a planet of simple organisms into one capable of animals, intelligence, and eventually, observers looking back across deep time. The history of complex life is often described as a steady ascent, a gradual progression from simple organisms toward greater diversity and sophistication. Yet, when we examine the fossil record closely, a different pattern emerges. Advancement was repeatedly interrupted, entire ecosystems vanished, dominant groups disappeared. Evolution did not move forward along a straight path. It was forced to begin again, over and over. The first Great Reset arrived around 445 million years ago. During the Ordovician extinction, roughly 85% of species disappeared. Geological evidence points toward a rapid glaciation that transformed global climates and lowered sea levels dramatically. Some researchers have also explored the possibility of a nearby gamma ray burst contributing to environmental stress. Whatever the exact sequence, the result was devastating. Life contracted sharply. Millions of years later came the late Devonian extinction. Around 375 million years ago, approximately 75% of species were lost. Unlike some extinction events, this one remains difficult to explain with certainty. Evidence points toward oxygen depleted oceans, known as ocean anoxia, where marine environments lose the oxygen required for most complex organisms. Asteroid impacts and prolonged volcanic activity remain candidates as well. The uncertainty itself is revealing. A planet does not require a single catastrophic trigger. Several smaller disruptions can overlap, gradually destabilizing ecosystems until collapse becomes unavoidable. Recovery followed, but recovery always required time. Then came the greatest disaster of all. About 252 million years ago, the Permian Triassic extinction reshaped Earth more profoundly than any other known biological crisis. Approximately 96% of marine species vanished. Around 70% of terrestrial vertebrate species disappeared as well. The leading explanation involves the Siberian traps, an immense volcanic province that released vast quantities of carbon dioxide and sulfur dioxide over roughly 60,000 years. The consequences spread everywhere. Oceans warmed, atmospheric chemistry shifted, food webs collapsed. For a period, complex life approached the edge of complete destruction. Another reset arrived near 201 million years ago. The Triassic-Jurassic extinction eliminated roughly 80% of species. As ecological niches emptied, dinosaurs expanded into roles previously occupied by competing groups. Evolutionary opportunities emerged from catastrophe. But even dinosaur dominance was temporary. 66 million years ago, an asteroid, approximately 10 kilometers wide, struck near present-day Mexico. The Cretaceous-Paleogene extinction followed. Dust and aerosols altered global climate. Photosynthesis declined, food chains failed, non-avian dinosaurs disappeared from the planet. A different future became possible. For more than 100 million years, mammals had remained comparatively small and ecologically limited. After the extinction, surviving mammalian lineages diversified into newly vacant environments. Much later, primates emerged from those branches, followed eventually by us. What stands out across all five events is the timescale of recovery. Each extinction erased complexity far faster than complexity could return. Rebuilding ecosystems required tens of millions of years. On another world, repeated catastrophes without similarly successful recoveries might prevent advanced life indefinitely. The ingredients could all be present, the biology could begin, evolution could advance, and still the clock might be reset again before complexity ever gains a lasting foothold. A layer of rock in southern China preserves a haunting boundary in Earth's history. Below it lies a thriving world of diverse marine ecosystems. Above it, much of that diversity is gone. The transition occupies only a thin slice of geological time, yet it marks the most devastating biological crisis our planet has ever experienced. It happened around 252 million years ago. Among all known extinction events, the Permian Triassic catastrophe stands apart. Earlier extinctions were severe. Later extinctions would reshape entire ecosystems. But this one approached a threshold beyond which recovery itself became uncertain. The source was not an asteroid. Deep within what is now Siberia, enormous volcanic eruptions began pouring molten rock across the landscape. These eruptions created the Siberian Traps, one of the largest volcanic provinces ever identified. Over time, lava spread across an area comparable to Europe, burying vast regions beneath layer after layer of basalt. The scale was extraordinary. For roughly 60,000 years, volcanic activity released immense quantities of carbon dioxide into the atmosphere. Current estimates suggest around 170,000 gigatons entered the climate system. Geological processes that normally unfold gradually became compressed into a comparatively brief interval. The planet responded. Global temperatures climbed by approximately 8 to 10 degrees Celsius. Tropical ocean waters near the equator may have reached 40 degrees Celsius, approaching the physiological limits tolerated by many marine organisms. Habitats that had remained stable for millions of years began changing faster than ecosystems could adapt. But warming was only part of the crisis. As carbon dioxide concentrations increased, seawater chemistry shifted. Ocean acidification intensified, a process in which seawater becomes more acidic and less favorable for shell-forming organisms. Creatures dependent on calcium-rich shells struggled to survive as environmental conditions deteriorated around them. At the same time, oxygen levels fell. Ocean anoxia, meaning severe oxygen depletion in marine environments, spread across enormous regions. Vast stretches of water became increasingly hostile to complex life. Food chains weakened. Ecological networks fractured. Species already stressed by warming and acidification faced another escalating challenge. Losses mounted rapidly. Approximately 96% of marine species disappeared. Around 70% of terrestrial vertebrate species vanished as well. Entire evolutionary branches ended. Ecosystems that had developed over immense spans of time collapsed within a geological instant. Yet perhaps the most revealing detail came afterward. Recovery required roughly 10 million years, longer than the recovery period following any other major extinction. Life returned, but only gradually. Evolution had to rebuild ecological relationships, restore biodiversity, and generate entirely new communities from a greatly diminished foundation. That long recovery invites an uncomfortable thought. Some researchers have suggested that slightly greater volcanic intensity, or a somewhat slower biological rebound, might have altered Earth's trajectory permanently. A world with fewer oceans, weaker climate regulation, or less biodiversity entering the crisis could have crossed a critical threshold from which no meaningful recovery emerged. As we widen our perspective beyond Earth, the lesson becomes difficult to ignore. Geological activity often makes habitability possible, driving atmospheric renewal and planetary evolution. But the same interior forces can become destructive on a planetary scale. A living world may survive impacts, climate shifts, and biological upheavals, yet still find itself threatened by the processes operating beneath its own crust, where the engines of creation and destruction are often the same. Imagine a planet that does everything right during its formation. It gathers rock and metal, survives violent collisions, develops a stable structure, and begins its existence much like countless other worlds. Then gravity intervenes. A close encounter with a larger planet alters its trajectory, and within a relatively short span of cosmic time, it is thrown outward forever. No star remains. These objects are known as rogue planets, planetary bodies no longer bound to any parent star. They travel alone through interstellar space, following dark paths between the stellar systems scattered across the Milky Way. Unlike the worlds we usually imagine, they do not circle a sun. They have no sunrise, no seasonal cycle, and no steady source of external energy. Their exile is permanent. Theoretical models of planetary formation suggest that ejections are common. During the chaotic early stages of a system's development, giant planets migrate, gravitational interactions intensify, and smaller worlds are often displaced. Some collide with neighboring bodies. Others fall into their stars. A significant number are simply expelled. Many never return. Current estimates indicate that rogue planets may number in the billions across our galaxy. Some studies suggest their population could rival or even exceed the number of stars themselves. A microlensing survey published in 2021 provided evidence that Earth mass rogue planets may be particularly abundant. Microlensing, a technique that detects objects through the bending of light by gravity, remains one of the few ways such hidden worlds can be found. Detection is difficult. A rogue planet produces no transit signal because it crosses no visible stellar disk. Reflected starlight is largely absent. Traditional exoplanet surveys depend on stars. These worlds have none. Most drift unseen through distances so vast that their existence is inferred only indirectly. Conditions on their surfaces are extreme. Without incoming stellar energy, temperatures plunge toward absolute zero, the theoretical limit where molecular motion nearly ceases, water freezes, atmospheres collapse. Surface environments become hostile beyond comparison with anything on Earth. But the story may not end there. Several researchers have proposed that certain rogue planets could preserve internal warmth for extraordinary lengths of time. Radioactive decay within their interiors generates geothermal heat. If a planet possesses a sufficiently thick hydrogen atmosphere, that atmosphere could act as an insulating blanket, trapping energy that would otherwise escape into space. Unexpected possibilities emerge. Beneath kilometers of ice, subsurface oceans might remain liquid. Chemical interactions between rock and water could continue. Environments isolated from the surface could persist for billions of years, protected from the frozen conditions above. These scenarios remain speculative, yet they expand the boundaries of what habitability means. We often picture life flourishing under sunlight, surrounded by open oceans and stable climates. Rogue planets challenge that assumption. They suggest that biology, if it exists elsewhere, may survive in places entirely detached from stars. As we consider the vast inventory of worlds scattered through the galaxy, some may have died before life began. Others may never have possessed the conditions we recognize as favorable. But a few could occupy a stranger category altogether, hidden between the stars, carrying isolated oceans through endless darkness, beyond the reach of almost every method we have to find them. Consider a simple question. What if the universe was not late in producing worlds like Earth, but early? The assumption that we arrived near the middle of the story is deeply intuitive. Yet modern astronomy increasingly points toward a different possibility, one in which complex, life-bearing planets may belong to the opening chapters rather than the mature ones. To understand why, we have to return almost to the beginning. The universe is approximately 13.8 billion years old. Earth formed around 4.5 billion years ago. That sounds relatively recent, but the first several billion years of cosmic history were fundamentally unsuitable for planets like ours. The reason was chemical. The earliest stars, known as population 3 stars, emerged within a few 100 million years after the Big Bang. They formed from almost pure hydrogen and helium, the only significant elements created in the primordial universe. Carbon was absent, oxygen was absent, iron, phosphorus, silicon, and the other ingredients required for rocky planets did not yet exist in meaningful quantities. There was nowhere for Earth to form. Those first stars lived brief and violent lives. Many were enormously massive, burning through their nuclear fuel rapidly before exploding as supernovae. Inside their cores, heavier elements were forged through stellar fusion. During their deaths, those elements were scattered across surrounding space. A new cosmic cycle began. Subsequent generations of stars inherited those materials. Each stellar generation enriched the galaxy further, increasing what astronomers call metallicity, the abundance of elements heavier than hydrogen and helium. Over billions of years, carbon accumulated, oxygen accumulated, iron became more common. Planet-forming material slowly transformed from primitive gas into something capable of producing complex worlds. The process was gradual. Evidence suggests that roughly 9 billion years of stellar evolution passed before conditions resembling those required for Earth became widespread. Only after countless stars had lived and died did the raw ingredients become sufficiently distributed to support abundant rocky planets with diverse chemistry. That places our planet in an interesting position. Earth formed during what astronomers sometimes describe as the age of terrestrial planets, the era when metal-rich rocky worlds become increasingly common. We are not located at the end of that period. We appear to be relatively close to its beginning, but the implications reach further. Many stars forming today will survive for tens of billions, and in some cases, trillions of years. Red dwarfs, despite their challenges, burn extraordinarily slowly. Future galaxies may contain vastly more opportunities for planet formation and biological evolution than have existed so far. The habitable era may be opening rather than closing. This perspective changes how we interpret cosmic silence. If complex life requires heavy elements, long planetary stability, and billions of years of uninterrupted evolution, then the earliest worlds faced significant disadvantages. Metal-poor planets may have struggled to assemble the chemistry required for sophisticated biology. Harsh conditions could have limited their potential from the start. Seen through that lens, Earth's existence may not indicate that life is common and hidden. It may indicate that we belong to one of the first generations of worlds truly equipped for complexity. When you look into the darkness between the stars, the apparent emptiness may reflect timing as much as rarity. A universe whose most fertile biological ages are still unfolding ahead. Imagine standing on a shoreline and hearing nothing beyond the waves. No voices, no distant signals, no evidence that anyone else is there. The silence itself begins to acquire meaning. After everything we have considered, every filter, every collapse, every planetary failure, we arrive at a different class of explanation, one that does not begin with dead worlds at all. Some researchers have suggested that life may be abundant. Hidden, perhaps. The zoo hypothesis proposes that advanced civilizations already know we exist. In this view, Earth resembles a protected preserve, observed but intentionally left undisturbed. Just as wildlife researchers avoid influencing the behavior of animals under study, a sufficiently advanced society might choose non-interference as a guiding principle. We would remain unaware of the observers because revealing themselves would compromise the experiment. It is an intriguing possibility. You can see why it persists. The idea preserves a populated universe while accounting for the absence of contact. Radio telescopes hear nothing because nobody wishes to be heard. Signals never arrive because they are deliberately withheld. The silence becomes a decision rather than a mystery. But another proposal reaches a darker conclusion. The dark forest theory, popularized by the novelist Liu Cixin, begins with a simple assumption. Every civilization values survival. Resources are finite. Intentions are unknowable across interstellar distances. Under those conditions, announcing your existence becomes dangerous. The universe becomes a forest at night. Every civilization moves carefully. Every signal risks detection. Every detection carries uncertainty. If another society possesses superior technology, waiting could be fatal. In such a framework, remaining hidden becomes the safest strategy. Communication disappears. Expansion slows. The galaxy fills with listeners who refuse to speak. Game theory, the mathematical study of strategic decisions, provides the foundation for this reasoning. Yet, even if the logic appears internally consistent, it introduces its own challenge. For the dark forest to explain the cosmic silence completely, civilizations separated by immense distances and billions of years must independently reach remarkably similar conclusions. That is a demanding requirement. The zoo hypothesis faces a related problem. Countless societies would need to maintain restraint across cosmic timescales. A single exception could expose the entire arrangement. One curious explorer, one reckless transmitter, one civilization choosing a different path, and the silence would break. But it has not. As we follow these possibilities to their edges, a simpler explanation remains waiting. It requires no coordination, no shared philosophy, no universal code of conduct. It asks only that the filters we have explored are genuine barriers and that most worlds fail one of them. Perhaps many never form properly. Perhaps life rarely begins. Perhaps complexity seldom emerges. In a universe approximately 13.8 billion years old, containing hundreds of billions of stars in our galaxy alone, the absence of evidence cannot prove absence. Yet when opportunity is measured on such enormous scales, continued silence becomes information in its own right. We cannot know what lies beyond our horizon. We can only acknowledge that after all this time, the sky remains unanswered. Consider a lottery with trillions upon trillions of tickets. One ticket wins. From the perspective of that winning ticket, the outcome feels astonishing. Yet the existence of a winner was never surprising. As our journey through planetary failures, biological bottlenecks, and cosmic hazards continues, we arrive at an idea that asks us to reconsider the way we interpret our own existence. This idea is called the anthropic principle. At first glance, it seems almost too simple. Its weak form states that we observe the universe we do, because only a universe compatible with observers could ever be observed. If a particular set of conditions were hostile to life, there would be nobody present to notice them. The statement appears circular. In a sense, it is. But circular does not mean useless. Suppose that among a trillion worlds, only one develops complex life. The inhabitants of that lone world would look around and find a remarkable sequence of coincidences. Their planet would possess the right chemistry, the right history, and the right environmental stability. They might be tempted to conclude that such conditions must be common. Yet their existence would guarantee that conclusion appears plausible. We can only find ourselves on a world where the requirements were met. Every failed planet lacks observers capable of reflecting on failure. Every sterilized biosphere remains absent from the conversation. Every world that lost its atmosphere froze permanently, overheated, or stalled in microbial simplicity contributes nothing to the sample available to us. Only survivors can ask questions. That perspective changes how we interpret Earth. Throughout this story, we have encountered a chain of circumstances that appear unusually favorable. A stabilizing moon emerged from a colossal impact. A magnetic field endured for billions of years. Plate tectonics regulated climate across immense spans of time. Giant planets occupied positions that reduced catastrophic bombardment. Biological transitions occurred that may have been extraordinarily improbable. Each event narrowed the path, but the anthropic principle cautions us against treating our presence as evidence that the path was wide. We stand at the end of the successful route, looking backward through conditions that happened to work. What would any observer discover if they traced their own history? The answer is unavoidable. They would always uncover a sequence that permitted their existence. That does not tell us how many failures surrounded it, nor does it reveal whether complex life is common or vanishingly rare. A universe filled with civilizations and a universe containing only one could produce observers asking the same questions. The principle cannot distinguish between those possibilities. It merely reminds us that observation carries a built-in bias. And so the lesson is subtle. The apparent improbability of Earth does not disappear. The moon, the oceans, the atmosphere, the timing, the geology, and the long chain of survivals remain extraordinary. The anthropic principle simply suggests that we are here to notice those alignments precisely because they aligned. Had any essential piece failed, there would be nobody left to wonder why everything seemed so unlikely. Long before Earth existed, before oceans formed, before the first cell divided, the ingredients of life were already traveling through the universe. They were scattered across expanding clouds of gas, drifting between generations of stars, carrying a history far older than any planet we have discussed. To understand what life is, we first have to understand where its atoms came from. The story begins inside stars. In their cores, immense pressure forces hydrogen nuclei together. Nuclear fusion, the process of combining lighter atoms into heavier ones, transforms hydrogen into helium. As stars age, new stages follow. Helium becomes carbon. Carbon becomes oxygen. Oxygen contributes to the creation of neon and heavier elements. Layer by layer, stars act as cosmic furnaces, manufacturing the raw materials from which planets, oceans, and living organisms eventually emerge. Nothing is wasted. Yet even stars have limits. Elements up to iron can be forged through fusion, but heavier substances require conditions far more extreme. Gold, uranium, iodine, and many other familiar elements are created during catastrophic events. Some emerge during supernova explosions, the violent deaths of massive stars. Others are born when neutron stars collide, releasing energies so immense that entirely new atomic structures can form. The universe builds patiently. When those stars die, their contents are thrown outward. Vast clouds of enriched gas expand into surrounding space. Over millions of years, gravity gathers that material again. New stars ignite. New planets assemble. Ancient atoms begin another journey. The carbon produced in one generation becomes part of another. The cycle continues across billions of years. And eventually, some of those atoms arrive here. The iron carried through your bloodstream originated inside a star that vanished long before the sun existed. The calcium within your bones shares a similar ancestry. Every breath you take contains oxygen forged in stellar interiors billions of years ago. These are not metaphors. They are consequences of nuclear physics unfolding across cosmic timescales. This is what Carl Sagan meant when he said, "We are made of star stuff." The phrase endures because it is literally true. As we trace these histories backward, the distinction between biology and astronomy begins to soften. Life does not introduce new matter into the universe, it rearranges existing matter into new forms. The atoms composing forests, oceans, animals, and civilizations existed long before any living thing appeared. They passed through nebulae, stars, planetary collisions, volcanic eruptions, and geological cycles before briefly becoming part of a living world. But those same atoms exist elsewhere. Dead planets contain carbon, frozen worlds contain oxygen, rogue planets carry iron and silicon through interstellar space. The material is not unique, the chemistry is widespread. What appears rare is the sequence itself, the timing, stability, and extraordinary chain of circumstances that allowed ancient stellar debris to organize into something capable of awareness. And so, after everything we have explored, we arrive at a remarkable realization. The cosmos did not stand apart from life and then create it. Life emerged from the cosmos directly, a temporary arrangement of ancient atoms that gained the ability to look back at their own origins and recognize where they came from. At the end of a long investigation, there is often a moment when scattered clues begin to form a single picture. Not certainty, not proof, just a pattern emerging from many independent pieces. As we gather together everything we have encountered, from planetary formation to biological complexity, we arrive at one of the most influential attempts to explain why the universe appears so empty. In 2000, paleontologist Peter Ward and astronomer Donald Brownlee presented what became known as the rare Earth hypothesis. Its central claim is straightforward. Microbial life may be widespread, complex life may not be. The distinction matters. A planet covered in bacteria and a planet producing civilizations are separated by an immense chain of requirements. As we have seen, habitability is not one condition, it is a sequence. Each step narrows the path. Each success depends upon earlier successes surviving long enough for the next threshold to appear. The hypothesis attempts to catalog those thresholds. A suitable region of the galaxy, a stable star of the proper mass and age, a rocky planet occupying the correct orbital distance, long-term climate regulation, a protective magnetic field, sufficient planetary mass, geological activity, atmospheric stability, a large moon capable of moderating axial variations, giant planets positioned to reduce catastrophic impacts, biological transitions that may themselves represent rare events. None of these requirements appears impossible. Taken individually, many seem entirely reasonable, but probability changes when conditions accumulate. Every additional requirement reduces the number of worlds that satisfy all previous requirements simultaneously. A rare outcome can emerge even when each individual step is relatively common. That observation forms the foundation of the argument. Yet the hypothesis remains controversial. Critics point out that every example comes from a sample size of one. We know only Earth. Life elsewhere may follow pathways we have never imagined. Different chemistries, different environments, and different evolutionary histories could produce complexity through routes unavailable on our world. That objection deserves respect. Science advances by challenging assumptions. History contains many examples where nature proved more inventive than expected. We should remain cautious whenever we attempt to generalize from a single case. The universe has surprised us before, but there is another piece of evidence that refuses to disappear. The silence remains. If complex life routinely emerges through many alternative routes, then over billions of years we might expect some visible sign, a signal, an artifact, a detectable civilization, something. Instead, every observation continues to return the same answer: stars, planets, vast distances, no confirmed evidence of technological societies beyond Earth. The rare Earth hypothesis does not claim victory because of that silence. It simply notes that the absence of evidence is consistent with its expectations. It remains one possible explanation among several. Perhaps not the final answer, but a parsimonious one, meaning it explains the available observations with relatively few assumptions, and the observations themselves remain remarkably simple. A universe containing countless worlds, and so far, only one known world where the universe has become aware enough to ask why. Picture a chain stretched across billions of years, not a chain of certainty, but a sequence of survival. Each link represents a threshold that could have ended the story long before anyone existed to tell it. As we gather those links together, the scale of what Earth has navigated begins to emerge. The journey started in violence, a young planetary system filled with collisions, gravitational upheaval, and competing worlds. Countless bodies never survived that stage. Some shattered, others were ejected into interstellar space. Earth remained. Then came the era of bombardment, when asteroids and comets crossed the inner solar system in vast numbers. Impacts reshaped surfaces across multiple worlds, yet somehow our planet endured that period as well, aided in part by the presence of a giant neighboring planet whose gravity altered the paths of many incoming objects. The sequence continued. A magnetic field emerged from Earth's molten interior. That invisible shield reduced the loss of atmosphere to space. Elsewhere, we have seen what happens when such protection fades. Mars provides the example. Earth followed a different path. Atmospheric chemistry then faced another challenge. A younger sun produced less energy than it does today, yet liquid water persisted. Conditions balanced within a narrow range where freezing was avoided without triggering runaway heating. The margin was small. Global glaciations followed. Ice advanced across much of the planet. Volcanic activity gradually restored atmospheric warmth. The cycle repeated. Earth escaped each frozen episode. Then biology introduced its own crisis. Oxygen accumulated in an atmosphere previously dominated by very different gases. Ecosystems collapsed. Recovery required hundreds of millions of years. Life endured anyway. A single cellular partnership crossed the threshold into complexity. One ancient event produced the mitochondrion, the energy-generating structure present throughout complex life today. Without that transition, the story likely ends in microbial simplicity. Yet the transition occurred. Later came mass extinctions. 5 times complexity approached catastrophe. 5 times ecological systems rebuilt themselves from what remained. The pattern is striking. A suitable star, a favorable position within the galaxy, long-term tectonic activity, a large moon helping stabilize axial behavior, oceans that persisted, an atmosphere that remained, a biosphere capable of adaptation. None guarantees success alone. Together they formed a sequence that continued long enough for intelligence to emerge. The probabilities are difficult to calculate, but their accumulation matters. Every filter crossed allowed the next challenge to appear. Every survival opened the possibility of another. Looking backward, The chain seems almost impossibly delicate. Looking forward from the beginning, there was no promise any link would hold. This is not evidence that the universe favors Earth. Nothing in the record suggests preference. The forces shaping planets operate without intention. Gravity does not choose. Stars do not plan. Evolution does not anticipate outcomes. The universe remains indifferent to success and failure alike. That may be the most remarkable part. Earth is not extraordinary because special rules were written for it. Earth is extraordinary because, across billions of years of indifferent physics and chance, the chain never broke. Many worlds likely encountered similar trials. They were made from the same cosmic ingredients. They simply did not receive the same sequence of outcomes, and the universe offers no opportunity to begin again. There is a tendency to imagine habitability as a permanent achievement. Once a world develops oceans, ecosystems, and intelligent observers, we instinctively treat those things as enduring features. Yet every stage of this journey has pointed toward a different conclusion. Conditions that allow complexity to emerge are temporary. They persist for a while, then they change. Earth is no exception. The same star that made life possible is slowly altering the terms of that possibility. Since its formation roughly 4.5 billion years ago, the Sun has steadily increased in luminosity. It brightens as hydrogen accumulates into helium within its core, changing the balance between gravity and energy production. The process is gradual, almost imperceptible, but over immense spans of time, gradual changes become decisive. Future geology has already been outlined. In approximately 500 million years, atmospheric carbon dioxide concentrations are expected to fall below the threshold required by most plants using carbon-3 photosynthesis, the pathway responsible for sustaining much of Earth's present biosphere. Forests disappear, food webs unravel, complex ecosystems begin contracting long before oceans vanish. The planet remains inhabited, but the range of life narrows dramatically. The decline continues. Between roughly 1 billion and 1.5 billion years from now, increasing solar output is expected to trigger a moist greenhouse state. Water vapor accumulates higher in the atmosphere. Ultraviolet radiation breaks apart water molecules. Hydrogen escapes into space. Over time, the oceans themselves begin disappearing. What happened to Venus through a different route eventually reaches Earth as well. This is not a fringe hypothesis. It emerges directly from established models of stellar evolution. But geological futures are not the only ones worth considering. Measurements collected since the 19th century indicate that Earth's magnetic field has weakened by roughly 9% since 1840. The magnetic shield generated by motions within the liquid outer core remains strong enough to protect the planet today, yet its long history reveals continual fluctuations. Magnetic reversals, where north and south exchange positions, appear repeatedly throughout the geological record. Many have occurred at intervals of roughly 200,000 to 300,000 years. We are beyond that range now. No one knows whether a reversal is approaching or whether current trends represent something less dramatic. During reversals, magnetic protection weakens temporarily, allowing greater exposure to charged particles from the sunday. Life has survived previous events, yet they remind us that even seemingly permanent planetary systems are dynamic rather than fixed. Then there is a newer variable. For billions of years, every filter we discussed emerged from astronomy, geology, chemistry, or biology. Now a species exists that can alter atmospheric composition, transform landscapes, redistribute resources, and influence extinction rates on a planetary scale. Intelligence has become part of Earth's environmental equation that introduces uncertainty. The long future remains measured in millions and billions of years. Human history occupies only a tiny fraction of that span. Yet, for the first time, one of the forces shaping a world's fate can contemplate the consequences of its actions. Earth will eventually join the ranks of dead worlds. The remaining question is whether that chapter arrives solely through cosmic inevitability, or whether intelligence chooses to accelerate the timetable. The story ends with an arithmetic problem so large that the mind struggles to hold it. Over approximately 13.8 billion years, stars ignited, galaxies assembled, planets formed, and countless worlds emerged from disks of gas and dust. Many never possessed liquid water. Many that did lost it. Others endured long enough for chemistry to become more intricate, only to stop there. Across cosmic history, planet after planet entered existence and then faded into geological stillness. A trillion opportunities, perhaps more. Yet here we are. Among all those worlds, one small planet orbiting an ordinary star carried an unbroken sequence of survivals. No single event guaranteed the outcome. The chain held because every link held. Atmospheres remained when they could have vanished. Oceans endured when they could have boiled away or frozen permanently. Evolution crossed thresholds that may have been extraordinarily difficult. Recovery followed catastrophes that might easily have become endings. The margins were narrow. As we have seen, the dead worlds are not merely distant curiosities scattered through the darkness. They provide a reference frame. They show us what the universe looks like when one requirement fails, when timing slips, when a climate tips too far, when a magnetic shield weakens beyond recovery, or when biology never reaches the next step. By studying those outcomes, we gain a clearer picture of our own. Earth stands in that contrast. Every extinction event preserved enough survivors for complexity to continue. Every climatic crisis eventually found a path back toward habitability. Every astronomical danger passed without permanently closing the window. Looking backward across billions of years, you can see how many alternate histories were available. Most lead elsewhere. Somewhere beyond our reach, there may be a planet where a giant impact unfolded differently, leaving no stabilizing moon behind. Another may have possessed oceans and continents, yet lacked the geological machinery needed to regulate its atmosphere. On another world, life may have emerged and then disappeared before complexity arrived. There could even be planets where intelligence almost appeared, only to lose its opportunity through circumstances we cannot reconstruct. We do not know. That uncertainty remains one of the defining features of our age. Telescopes continue searching, probes continue exploring, observatories continue examining distant atmospheres for hints of biology. But regardless of what future discoveries reveal, one fact remains unchanged. The material that makes you has a far older history than Earth. The carbon in your cells, the oxygen you breathe, the calcium within your bones, and the iron carried through your blood were forged long before the sun existed. Those atoms traveled through ancient stars, expanding nebulae, interstellar clouds, and forming worlds. They participated in stories that ended billions of years ago. Now they participate in this one. For a brief interval, measured against cosmic time, they have become part of something capable of asking where it came from and what surrounds it. That interval will not last forever. No world escapes change indefinitely, but it exists now. And in a universe filled with worlds that never reached this moment, that fact carries a significance all its own.